All right, we are looking at section 5.3, page 337. 5.3, page 337, the fundamental theorem of calculus. It's finally here. All right, on page 337, they go through and describe the fundamental theorem of calculus to you. But in essence, we study two different branches of calculus. We study differential calculus, which is the calculus of derivatives, and we study integral calculus, which is the calculus of integration. There is a relationship between those two branches, and in essence, the fundamental theorem shows us how those two are linked and related. And we're going to find out that derivatives and integrals are just inverses of each other. We saw a little bit of that in 410 with the idea of an antiderivative undoing a derivative with an indefinite integral. Today we want to see how a derivative and a definite integral can also be linked together. And the best part about this, the reason why we literally are going to stop and party and celebrate, is we're going to get a super shortcut for finding the area under a curve, the exact area under the curve. So instead of having to do that crazy limit of summations that we did in sections 5.1 and 5.2, with left, right endpoints, midpoints, the Riemann sums that were the approximations, and then the actual areas under the curve where we had to go through and do the infinite number of limits, and we put in the change in x and x sub I and come up with the crazy summation formulas and then replace those with their definitions and take the limit of that whole thing, you know, the thing that takes like half of a piece of paper to do one problem. We're going to be able to do it in one line now and literally do that problem in about 15 seconds instead of 10 minutes. Okay? So, the fundamental theorem of calculus on page 338 is actually in two separate parts. The first part, not so exciting. The second part is the exciting part, so hang in there. All right, so first part of the fundamental theorem of calculus tells us this. If the function is continuous, that's pivotal, right? Because that's the prerequisite for everything since we've learned continuity. If your function is continuous on the interval, then g of x is equal to the integration from a to x of f of t dt. If your function is defined in that way and it's continuous on the interval, the closed interval, differentiable on the interval, the open interval, then the derivative of g of x will be equal to f of x. That's their kind of concluding statement down there. Now, let's see how that first statement and that last statement are linked together. If g of x would be the integration of f of t dt from a to x, if I were to go through and insert a derivative on each side, all right, the derivative and the integral will cancel each other out and just leave me with the function. But look what happens. When I'm taking the derivative in terms of x of this function that was in terms of t, notice that the t gets replaced with x. That is the first part of the fundamental theorem of calculus. And so that's where they get their concluding statement down here, that the derivative of g of x is equal to f of x. Rather than, remember our starting statement up here was if you integrate f of t, notice their concluding statement was not that you get f of t, you get f of x. That's the key that they're trying to purport in that first part. So if you take the derivative of an integral, it's going to be in terms of, thank you, whatever variable it's in terms of, in this case it was in terms of x, then that replaces the variable in my function. And so I ended up with f of x, not f of t. So the first part of the fundamental theorem of calculus said that if g of x is equal to the integration from a to x of f of t dt, then your answer for the derivative of that would be f of x, not f of t. Now, in terms of kind of helping us understand how that's possible, you know, we've done a little bit of the legwork up here. If g of x is equal to the integration of f of x, then I could go back and say, okay, then g of x would have to be equal to the integration of the derivative of g of x, because f of x was the derivative of g of x. So in essence, we're reestablishing what we said in 410, that if you integrate the derivative, you go back to the original function. And that idea of indefinite integral being an antiderivative, a little bit of a restatement of that. But the key that we want to get from the first part is that idea that if you integrate a function, you have to replace the variable in that function. So look at example number 1. We've got g of x is equal to the integration from 0 to x of the square root of 1 plus t squared dt, and they ask us to take the derivative of that in terms of x. So I'm going to go through and take the derivative in terms of x. When I take the derivative of an integral, they'll cancel each other out as long as these variables are the same. Like, I can't take the derivative in terms of x of an integral that goes from 0 to t, right? So I need these variables to be the same. Derivative in terms of x from 0 to x. So, okay, the derivative and the integral will cancel each other out. And remember the little notation over here that always goes with the integral. I can drop that out. Then all that I'm left with is my function. But notice the function has changed. Instead of being the square root of 1 plus t squared, it is the square root of 1 plus x squared, because I took the derivative and the integration in terms of x. All right, look at another one. For the next one, we've got the derivative from 1 to x of secant t dt. So the derivative and the integral are both in terms of x. They'll cancel out. And I'll get my original function, which was secant, but notice it's no longer in terms of x. It's no longer in terms of t, it's in terms of x. All right, let's take a rabbit trail here for just a second. Remember when we did chain rule with derivatives, okay? Like if I had the derivative of sine x cubed, we were not allowed to take the derivative of a quantity, so we had to use u substitution. So we would go through and we would say, okay, let's let u be equal to the quantity, since that's what's causing us trouble. And so then we would be left with just the derivative of sine u. Well, in order to do that, we would go through and we would say the derivative of sine u is cosine u, and then we would have to go back and take the derivative of the x cubed and get 3x squared. What we were doing was chain rule, and by definition, chain rule is the derivative in terms of u times the derivative of u in terms of x. Look at how that applied to this problem right here, because we went through and we took the derivative of sine u, and it was in terms of u, not in terms of x. So even though we're doing the derivative in terms of x, chain rule enables me to do the derivative of sine u in terms of u to get the cosine u. And then I go back and I take the derivative of u in terms of x. I take the derivative of what I had substituted out. So the derivative of u in terms of x. And so then I have to back substitute and go back and replace whatever was u with the x cubed. So we simplified that process down to say, let's take the derivative of the outside function times the derivative of the inside function, so we didn't have to go through and stipulate that u substitution after we did the first couple of these. But that was our original introduction to it and its definition. I want to remember that because when I get to example number 3, I'm supposed to be taking the derivative of the integral, but I have a problem. Because this is not just a plain x up here. I can't do the derivative in terms of x to the fourth. I can do the derivative in terms of x of x. So I'm going to have to use some u substitution. So I'm going to let u be equal to x to the fourth. So I'm going to rewrite this integral as the derivative from 1 to u of secant t dt. Now, if I'm going to do that, I need to, remember we said these variables have to be the same. I'm going to have to use chain rule. I'm going to have to say the derivative in terms of u, because if I took the derivative in terms of u, I'd be okay here, and then I'm going to need to multiply by the derivative of u in terms of x. All right, so I'm going to use chain rule, and I'm going to say the derivative of this integral in terms of u, so now these u's are okay. So I can do the derivative of my integral in terms of u, and then I'm going to need to multiply by the derivative of u in terms of x. All I'm doing is chain rule. So there are times that when I'm taking the derivative of an integral, if I have a quantity that I have to substitute out, then I'm going to use chain rule to do that. All right, so let's finish this off. Let's focus on this piece. The derivative and the integral will cancel each other out, and of course, the little notation here at the end goes with that, and I would be left with the original function, which is secant. But remember that I have to replace this variable with the variable that I was taking the derivative and integrating with. So I'm going to replace the t with u. Now I'm going to come over here and take the derivative of u in terms of x. Well, u was x to the fourth. So if I take the derivative of x to the fourth, I'm going to get 4x to the third, and that is in terms of x. So it kind of lays itself out. And then what I need to do is back substitute. I chose to put u in the place of x to the fourth, so I need to go back and put x to the fourth back in the place of u. And so in essence, I have the derivative of the outside function, which was my integral, times the derivative of my inside function. That is as complicated as they can get with the first part of the definition. All right, so let's look at the second part of the definition, because the second part of the definition is the happy thing. That's what makes us want to stop and have a party. Over on page 341, they start off with if the function is continuous. That's important. Then the integration from a to b of f of x dx will be equal to capital F of b minus capital F of a, where capital F of x is your antiderivative. Remember, that's the notation that they've used for antiderivative before. All right, so if we wanted to break this down into like a step-by-step process, number one, we're going to find the antiderivative, which is the capital F of x, like we were doing yesterday in section 410. And then we're going to plug in b and plug in a and subtract. Well, let me show you what I'm talking about. Let's say that we have example number 5, the integration from 0 to 1 of x squared dx, right? Step number 1, let's find our antiderivative. So what would the antiderivative of x squared be?
x3 over x to the third.
Yes, x cubed divided by 3, or 1/3 x cubed, however you want to write that. So we increased our exponent by 1 and we divided by that same number. So x to the third over 3, or 1/3 x cubed. All right. Now we're going to go back and we're going to plug in our b value, plug in our a value, and subtract. All right. So what do we get when we plug 1 into this thing? 1/3, right? What do we get when we plug in 0? 0. So we'll have 1/3 minus 0, which is 1/3, and I am done. Okay, you have to hang on for just a second and think about what that problem would have looked like in section 5.2. I would be sitting here and doing b minus a divided by n to get my change in x, right? So I'd have 1 over n for my change in x. And then I'd have to do f of x sub I. So that would be a plus the change in x times I. And then I would have to plug that into the function. And then I would have to do a summation where I broke it into separate pieces and moved the constant out in front and replaced the summation with its formula and took the limit. I mean, we're talking like a half page, right? I'm going to get to the point that I can do these in my head. I mean, that's going to take me 10-15 seconds. That is a happy thing. All right.
You have to do it both ways on the test.
Yes, we do have to do it on this first test. We do have to do it by the definition because that was 5.1 and 5.2, right?
I guess there's a way of checking, right?
And then we will be moving to doing it this way. Now, remember that you can only use this for something that you know how to take the antiderivative up, because first step is take the antiderivative. So if you had, we have so few antiderivative formulas right now, or integration formulas right now, that we would have to use long way for something we didn't have a formula for at this point. But we will get lots more formulas just like we did with derivatives. Okay, so here's the notation that we're going to use for this, because this is going to get cumbersome to sit here and write step number 1, step number 2. Here's the notation that we can use that is understood universally. And that is, I'm going to write my definite integral. In step number 1, right here, I've done the antiderivative, but I haven't plugged a and b in yet, because I don't want to try and do all that one time in my head, or I'll make careless mistakes, right? So this is, here's my antiderivative. I have yet to plug in a and b. Some books will use a straight line right here, and others will use a bracket right here. So we'll use a bracket with our textbook, but you'll see it sometimes written just as a straight line. So I can go through then and plug in 1 and then plug in 0 and write my answer. And so that's a succinct notation that shows the same thing as what we did up here. Now, we've mentioned before that when you work with an indefinite integral, an antiderivative, you're going to get an equation as your answer. But if you work with a definite integral, you're going to get a number as your answer. And that's exactly what happened right here. The only exception to that is something like what you'll see in example 6, where they don't have me integrating from 0 to a number. They have me integrating from 0 to a variable. In that case, then I am going to get a variable in my answer. I could end up with an equation instead of a value. Because, I still have a variable here instead of a precise value. I'm not saying find the area under the curve from 0 to 5. I'm saying find the area under the curve from 0 to some arbitrary value b. Okay? And that has its advantages as well. We'll see that in a second. So if I'm going through and I'm integrating cosine, what's the integration of cosine? Sine. And I've not plugged in my a and b values yet, right? So this is stating I've done my antiderivative, but I still need to plug in a and b. All right, so then I could go through and put in b and put in a and subtract. It's always b minus a. What is the sign at 0? 0. So that's going to drop out and just leave me with sine b. So here's the advantage of not putting in a number. Like if we had said find the integration from 0 to pi of cosine x, then we would only find the area under the curve from 0 to pi. But what we've done here is basically created an equation that we could go back now and say if I wanted to find the area from 0 to pi, I can just put pi right here. But if I wanted to find the area under the curve from 0 to 2 pi, put a 2 pi here. From 0 to pi over 2, put a pi over 2 here. So it basically has given me a formula that I could utilize for multiple values instead of just one precise value. All right, look at example 7. Example 7, they give me the integration of 1 over x squared dx from negative 1 to 3. I'm going to rewrite that as x to the negative 2 just so it's a little easier to do our power rule. All right, so what happens when I integrate x to the negative 2? What do I get?
Negative 1 over negative 1.
Yes, x to the negative 1 over negative 1. I'm going to rewrite that as negative 1 over x. Just a little easier for me to plug numbers in. Haven't plugged in a and b yet. All I've done is my antidifferentiation. All right, so now I can go through and plug in 3. So if I plug in 3, I'll get negative 1/3. And then plug in negative 1, so that would be negative 1 over negative 1. So I'd end up, if I plug in my negative 1 here, I'd end up with minus a positive 1. So I have negative 1/3 minus 1, I get negative 4/3. There is a problem with that.
You can have a negative area.
I can have a negative area, but when is the only time that I can have a negative area?
When it's underneath.
When my function is underneath the curve. Does this function graph underneath the curve? I don't know. Without my calculator, I don't have a clue what that graph says. Okay, think about it. Any value on the face of the earth that you plug in for x in this thing is going to become positive or negative? Positive. And 1 divided by positive is going to be positive, right? So I don't have to know what the graph looks like to know that 1 over x squared, every value I put in for that is going to be greater than 0. That means that whole thing will graph above the x-axis, which means I should be getting a positive area, but my answer is negative. There is some kind of problem here. What is it?
It's going from a big to a small number as it goes on.
Okay, but it would still be above the x-axis, so it should still be positive. What is the problem? What is the prerequisite for every single integral we do?
It's not defined.
It has to be continuous. Is this continuous?
No.
No. And it's an easy mistake to make to just automatically get so excited about, oh, 2 steps to the definite integral. I can do it so fast with the fundamental theorem of calculus, and I jump in and I get all the way to my answer and I write negative 4/3 and I move on. This does not exist. You can't find the area under the curve of something that's not continuous. If you go back and you look at this original function, x squared is in the denominator. That means at 0, this function does not exist. There is a hole in that curve. How do you find the area underneath something that's got a hole in it? I mean, I can't do that. So that's why the very first statement in every piece of this is if the function is continuous on the interval. This function is not continuous. So from the very outset, there's no need to even do this problem. my answer is going to be does not exist because it's not continuous. So here's a suggestion. If you'll notice, unless I happen to realize, hey, this is negative and this is positive, I would have thought there was nothing wrong with my answer and gone straight on, right? So it's a good idea, as soon as you get a test or a quiz, go through and look at every one of your integrals and just check every one of them for continuity. Because if you find one that's discontinuous, you can just go ahead and exit off and say does not exist in the answer blank and you're done, right? That's a freebie. Instead of maybe you missing that and taking the chance of spending extra time on it when you don't have to. So we always want to check for continuity first. Now, what if this had been the integration from 1 to 3 instead of from -1 to 3? What if it had been the integration from 1 to 3? It would have worked, yes, and the answer that I would have gotten would have been my solution. So just because the function has a discontinuity does not mean you can't integrate it. If the discontinuity is in your interval, you have a problem. But if it's not in your interval, you're fine. And we've seen that same kind of thing before where we had to check intervals, like, even with things like Rolle's theorem and intermediate value theorem, we had to go through and check continuity and differentiability before we could jump into it, okay? So make that a prerequisite for yourself with your integration. Look for continuity first before you jump in. Now, one last thing I want to mention to you. They don't really give you a theorem for this in the textbook or anything like that, but there are some problems like this that show up on the homework. And so I want to make sure that you understand it. And that is if you have to integrate a piecewise defined function. Now, if you're integrating an absolute value, that's a piecewise defined as well, right? You got to take your absolute value and define it in the separate pieces first. If you are finding the area under a curve and you have two separate curves, you have to have two separate pieces, right? You can't go through and find the area under f of x from 0 to b because I have a different function from a to b. I don't have f of x anymore. So there's no theorem for this. They kind of expect us to pick this up with logic and common sense, but I wanted to make sure that we talked about it. If you have the integration of a piecewise or an absolute value, you're going to need to redefine it in its pieces and then go through and say, okay, I need to find the area under the curve from 0 to a for f of x, and then I need to find the area under the curve from a to b of g of x, and once I get those two answers, I'll add them together. So that would be the integration from 0 to a of f of x plus the integration from a to b of g of x added together would give us our total area. All right, on 344, I don't often read from the book, but I'm going to read this to you. On 344, it says, the fundamental theorem of calculus is unquestionably the most important theorem in calculus, and indeed it ranks as one of the great accomplishments of the human mind. Before it was discovered from the time of Eudoxus, I don't know how you pronounce crazy Greek names, and Archimedes, to the time of Galileo and Fermat, problems of finding area, volume, and lengths of curves were so difficult that only a genius could meet the challenge. But now, armed with the systematic method that Newton and Leibniz fashioned out of the fundamental theorem, we will see in the chapters to come that these challenging problems are accessible to all of us. All right, here is your homework for tonight. On page 344, we are doing 1, 5, 9, 11, 19, 21, 23, 25, 29, 33, 39, challenge 49.